Good morning, girls. uh, Today we are going to discuss about the further definitions or to say things related to trees, right? So in the last class we have seen all these things like how you represent a tree in general, like it is a set of R and T. R is nothing but the root of the tree, and T1, T2 up to N are the number of subtrees of that particular node, and N represents the number of nodes, right? No, sorry, N represents the number of trees. So we have seen a tree without a root is called null tree, and the other one is zero tree, or which has only root, and this is an actual tree. Okay, so what is the degree of a tree? What are who are called children, parents, siblings? Okay, so these are the things we have all seen. Next, length, depth, height. Okay, so what is the length? The number of edges it contains. From the root to the last node. And what is the depth or level of a node? Length of the node uh, till the particular node to be where to which you want to calculate the depth, which is the length from a directed path from the root to that node. And the height is nothing but the longest path, the length of the path from the root or to a node at the lowest level. In other words, the maximum path length is called the height of the tree. Okay, so pre-order traversal, in order, post-order traversal. These are the three types of traversal we have. We will see them in detail in binary trees. Okay, so our discussion is going to be confined to binary trees after this today's class, because that is the only topic that we have to learn about trees. There are other kind of trees and other operations as well, but mostly we are going to learn about binary trees, because those are the trees which are mostly used in the calculations or our computers a lot. Next, so we have seen what subtrees are. See, so with respect to this diagram, we will see all these definitions, right? So what are subtrees? The nodes, these 2, 3, 4 are called subtrees. 5, 6, 7 are called leaf nodes. Why? Because there are no further children to these nodes, so these are called leaf nodes or terminal nodes. And 8 is again a subtree because it has given rise to 2 children. So 4 is a subtree in itself, and 8 is also a subtree in itself. See, so nodes 2, 3, 4 are the roots of the subtrees labeled 1. So these are the roots for the subtrees which further span from these nodes. Okay. Next, 5, 6, 7 are the roots of the subtrees, but here there are no further nodes, so they can be called leaf nodes or terminal nodes. And 8, if this 8 is also a subtree, 4 is a subtree, so further they can give rise to uh, children, then they will come under subtrees, right? Next, leaves. So the nodes which don't have any children or further nodes attached to them, then they are called leaf nodes. 2, 5, 6, 7, 9, 10, all these are leaf nodes. Next, what is the degree? Degree is nothing but the number of edges coming out of a particular node, or the in a directed tree we can consider the incoming edges and the outgoing edges in degree and out degree, and the degree is the degree of the node as a whole is nothing but in degree plus out degree of the node. Or when it is not a directed tree, you will consider only the number of edges which are coming out, or which are drawn from that particular node to the other nodes, right? So the degrees of nodes 1 and 3 are 3. See, but 3, you have 3 subchildren, subtrees. So the degree of 1 is 3, and the degree of 3 is also 3 because it has 3 leaf nodes attached to it. So the degree of this particular node is 3, and the degree of 8 is 2. So the number of edges which are coming out of those nodes will constitute the degree of that particular node. So all the leaf nodes have degree 0 because there are no other nodes coming from them out, so their degree is considered as 0. So the degree of the whole tree is 3 because the maximum degree, I mean number of edges coming out of one particular node, maximum number of edges, that is considered the degree of the tree as a whole. So here the degree of the tree is 3 because for 1 it is 3 nodes and for 3 also it is 3 nodes. We don't find any other node which is giving rise to more than those 3 edges. So is the degree of this particular tree is 3. Next, levels. Already we have seen the levels, like the length of the path from root to that particular node, the level of 4 or 2 or 3. These 3 nodes is 1 because they are at a distance of only one edge from the root node, and here the level of 8 node number 8 is 2 because it is at a distance of 2. It is a distance of 2 edges from the root node. So in this way you will calculate the level of a particular tree, and the height is nothing but the highest path or level or the depth of the tree is called the height of the tree. So the height of this particular tree is 3. The maximum path length here is 3. So 1, 2, 3. So that signifies the height of the tree. So family relationships. So I have told you in the last class. The 2, 3, 4 are siblings because all these span out from the node or root node 1, and 5, 6, 7 are called siblings. Because all these 3 come out from the same node 3. So 5 is sibling to 6 and 6 is sibling to 7. So all these 3 are siblings, but these 5, 6, 7 are not siblings to 2, or they are not siblings to 8. At least we will consider of this level, because 8's parent is not 3, it is 4, so they are not siblings. So only the nodes which come from the same node, which span from or take arise from the same node are called siblings. And here we call this as parent and these as children, ancestors. Like you have so many terms. Next, paths and path lengths. So what all the paths exist in this tree? See, this is one path, 1 to 2, and this is 1 to 3, 3 to 5, 1 to 3, 3 to 6, 1 to 3, 3 to 7. Okay, next 1 to 4, next 1 to 4, 4 to 8, 1 to 4 to 4 to 8 to 9. So these are the paths you have in this particular tree. So next, height and depth. Already we have seen the maximum level or the maximum length of the tree. The length of the path of the tree is called the height of the tree, and the depth also we have seen the length of the path from root to that particular node, to which node till you want to calculate the depth. That gives you the depth of the tree. So here these two nodes 9 and 10 are having the same depth as the height of the tree. So and here the height and depth are same for this level 3. And these are the things that you have to keep in mind. So this one thing you have to understand is the depth of the nodes or the lowest level is always the same as the height of the tree, because this is what is the lowest level. Lowest level means no further nodes are existing from that particular level, that is they are the leaf nodes or terminal nodes of that particular tree. Of that particular tree. So this becomes the, for this, if you calculate the depth of this particular node, this is the as this is the last node, so this will be the highest or lengthiest path of the tree. So automatically the longest path of the tree is called is given the height of the tree. Will give you the height of the tree. So this last node will give you the height of the tree. The depth of the nodes on the lowest level is always the same as the height of the tree, right? Next, orders. We have seen pre-order, in-order, and post-order. So we will see pre-order is nothing but we will be moving um, to towards all the nodes in balance. Like I'm not leaning towards left or not leaning towards right. So 1, 2, next 3, 4, next or 5. You're having nodes, sub nodes or child nodes for 3. So 5, 6, 7 are the sub nodes, and 9, 7, 9, 10 are the sub nodes. So in this way you will be traveling in balance, but in order always you will travel to the left subtree and then you will come to the right subtree. And post order always you will be traveling towards the right or the outmost nodes and then come to the inward nodes. Like see after 2 you will write 5, 6, 7 and then you write 3. Next you write 9, 10, 8, then you write 4. So this is how. So this is how, and the root comes in the last for the post order. So this is how we will see these orderings in detail in the next classes. So you have 3 types of orders: pre-order, post-order, and in-order. So representation of a general tree. So how you will represent a general a tree in a general. See, you can represent either in a sequential organization like arrays or whatever suite stacks, whatever you call, or a linked organization by using a linked list. So if we use a linked list, then there must be a varying number of fields depending on the number of branches. So the number of fields in the particular node will be varying depending on the number of branches a particular node will give rise to. So it is to use algorithms. It is very much easier to have a fixed size node. So we will at present consider a node of a fixed size. So this is how your tree is represented in a linked list. The data, link 1, link 2. I mean the next uh, links to the next nodes which arise from that particular node or which are having edges from that particular node. So this is how a fixed size node looks like. I mean it will have only 2 links, a link down and link next. Okay, so you are giving tag 1, a tags 0 or 1. I mean it is having further nodes or not, and it is the actual data which that particular node is going to store. And if it is having next, I mean, for the nodes arising out of it, it is having children. Next, they are represented here as link down and link next. See, this is how your sample tree looks like, and this is the linked list representation of that particular tree. So A is a node, right? So A is giving rise to 3 nodes: B, C, D. So it has 3 uh, children. So see, from A you will have 3 lists: 1, 2, 3. So 3 nodes. So one is representing to, one is pointing to B, and one is pointing to C, and one is pointing to D. So it is not having further, I mean, are just coming into it. So it is set as 0. Here it is set as 1 and B. So it is again its tag is set as 0. Okay, it is giving rise to two children. I mean E and next F. So link down and link next. So this is link down and link next. So link down and link next. So again the it is having 3 nodes: link down, I, H, and J. Okay, so these are not having any further nodes, so they are next links are set to 0. So for all the leaf nodes, the next links are set to 0. If they are having further nodes, they are represented as 1. Okay, so this is how you represent a tree in generalized representation of a tree. Next, types of trees. So these trees, we are just will see the definition of different kinds of trees that exist in uh, theory, but in our applications or computer applications, mostly we use binary trees. So we will be studying binary trees in detail. So we'll just see what these different kinds of trees are. So first, free tree. What is a free tree? So it is a connected acyclic graph. So in general, a tree is nothing but an acyclic graph which doesn't contain any cycles. It is a connected one. Yes, if it is not connected, then it doesn't form a tree. Okay, it is an undirected graph, so that no directions are specified. The main feature of this particular tree is no node is designated as root. So any node is not given that name as a root. So here every node is free. I mean, it is treated as independent node. No node is treated as a root. So what is the use of this particular tree is you can start traveling from any node to any other node. There is no need to that you have to start your traversal from the root itself. So that is the main feature of this free tree. Next, free tree. Next to free tree is rooted tree. So what is a rooted tree? One particular node is designated as a root. So per root there will be no incoming, no, I mean further edges coming to into the root. So the incoming degree of the node is 0, whereas for all other nodes it is 1. Say for this particular B, the incoming degree is 1, and for any particular tree, the incoming degree is 1. So in rooted tree, one particular node is designated as a root. That is why it is called as rooted tree. And ordered tree. So what is an ordered tree? So we give order. I mean, the give sorry we give numbers to the nodes in the trees so that we can specify that we have to travel only in these what do you say order. See, from 1 I have to go to 2, and then 3, next 4, 5, 6, 7, after 7 I have to go to 8, and next 9. So this is the order in which I have to travel from one node to the other node. So see, this will be like you are giving an order in which uh, I mean way or in which order you have to travel from one node to the other node. Just like we are specifying the order to the nodes, we can give orders to the edges also. So if in a directed tree an ordering of a node at each level is prescribed, then such a tree is called ordered tree. So along with the directions, if you also specify the order in which the nodes have to be traversed, then such a tree is called ordered tree. Next, regular tree. So what is a regular tree? See, a tree where each branch node vertex has the same out degree is called as a regular tree. So here it is not a regular tree because the out degree of 2 is 4 and the out degree of 3 is 2. So according to regular tree definition, each vertex should have the same out degree as the other nodes, and every node should have the same out degree, but this is not here. So this is not a regular tree. So if in a directed tree, the out degree of every node is less than or equal to m, then the tree is called an m array tree. So you give a number called m. M can be 2, 3, 4, like that. So for every node, the degree, I mean number of edges which are drawn out from that particular node is equal to m or less than m, then such a kind of tree is called m array tree. Okay, and if the out degree of every node is exactly equal to m or 0. So here we have seen it can be less than or equal to m. That is called only m array tree. If it is equal to m or it is 0, I mean no further nodes. Either it should be equal, I mean the two nodes should have the same number of children, or I mean edges, I mean out degree, or they should have only 0 as the, they should I mean leaf nodes, no further spanning of the nodes from the tree. Then such a tree is called regular M-array tree. So we have seen the definition. Regular all the nodes should have the same out degree. So nodes having the same number of degree which is equal to m, or no leaf, I mean no degree at all, I mean no further edges coming out of it, then such a tree is called regular tree. Next, binary tree. So a binary tree is nothing but an M-array tree, and it will have only two nodes coming out of it, no two edges coming out of it from it always. So that such a tree is called binary tree. So a binary tree is an M-array tree where m is equal to 2. Node has more than 2 children. So that is the condition of your binary tree. That is what we have to keep in mind. So a tree where no node is having children more than 2, no 2 children, or more than no 2 children, then it is called a binary tree. Next, complete tree. So what is complete tree? Say a tree with n nodes and of depth is complete if its nodes correspond to the nodes that are numbered from 1 to n in the full tree of depth k. So if all the if the tree is having uh, nodes, I mean nodes give rise to giving rise to children, I mean child nodes, and it, the depth of that particular tree is k, then that can be called as a complete tree. So a tree with n nodes and the depth k is complete if and only if its nodes correspond to the nodes that are numbered 1 to n in the full tree of depth k. So you have to number the trees, and the depth should be k, and all the nodes should be numbered from 1 to n. Then such a tree is called complete tree. So see here, left subtree and right subtree. So the height of the left subtree is h minus 1, and uh, height of the right subtree is h minus 2, and in any of these conditions it is called a complete tree. Either it is empty, or if the height of left subtree is less than, I mean greater than the right subtree, and the height of the left subtree is equal to the height of the right subtree. So you will call a binary tree as completely full, I mean a full tree, when it the height is h, and the number of nodes is 2 power h plus 1 minus 1. See, for example, h is equal to 2, 2 power 2 plus 1, that means 2 plus 1 is 3, 2 cube is 8, 8 minus 1, 7. So if height is 2, say, and the number of nodes should be 7, then uh, it is called a completely full binary tree. I mean, this condition has to be satisfied. Like it should have these many number of nodes. So full binary tree. So a binary tree is said to be a full binary tree if it contains a maximum possible number of nodes at all levels. So this is called full binary tree. So each node is having the maximum number of nodes it can have. And in general, the binary tree can have only 2 children. So each node is having only 2 children. So these are the leaf nodes. So it is, they are not having any children, but Here they are having the maximum capacity of nodes that they can give rise to. So this is called a full binary tree. So how will you calculate how it is going to be full? By using this expression 2 power h plus 1 minus 1. So complete binary tree. So a binary tree is said to be complete binary tree if all its levels except the last level have the maximum number of possible nodes. So except the last level. See, in the last level, the sixth node and seventh node is not having further nodes. They are empty. So it is not full, but it can be called as a complete binary tree as it is having the maximum number of nodes that can exist, and all those are having appearing on the left. So most of the nodes are always added to the left side of the tree. In such a case, it is called a complete binary tree, and always the levels are filled from left to right. So these what is the use of this complete binary tree is in mostly found in priority queue and heap sort. Okay, so this in your unit 4 we are going to study in detail about this heap sort. So this is what a complete binary tree is. So always the nodes are uh, attached to the left part of the tree, and maximum possible number of nodes are uh, there except in the last level. Next, left skewed tree. Left skewed tree is nothing but all the nodes will go on going on attached to the left part of the tree, and all nodes will go on getting attached to the right part of the tree. So in this, it is the right part is missing, and in this left part is missing. So left skew tree and right skew tree, these are the trees. Next, strictly binary tree. So uh, what is it? Strictly binary tree? See, if non-terminal node consists of non-empty left and right subtrees, then it is called strictly binary tree. See, for every non-terminal node, non-empty left and right subtree. So the left or right subtree should not be empty. See, here it is empty. So it is not a strict binary tree. It is only a complete binary tree. Here no node is there. I mean, is left empty in the left subtree or the right subtree. So then it is called left subtree. Strictly binary trees. Next, extended binary trees. Say a tree with each node having 0 true children is called extended binary tree, and the nodes with 2 children are called internal nodes, and 2 with 0 children are called external nodes. So it is nothing but a form of binary tree. And position tree. This tree is particularly used for manipulations of strings. So the edges of in the position tree will be having the suffixes of the strings representing the edges. So to locate a substring, or to find out the mistakes, or to find out the matches of that particular expression, we will be using this position trees. So these are the different varieties of trees that are available to us, but most commonly used and most popular one is the binary tree. So we will be seeing what a binary tree is, what are the properties of binary trees in detail in the next class. Okay, so if you have any doubts, ping me in the group calls.